Welcome back to the Deep Dive, everybody. Today we're going deep, really deep into the world of AI and how it's tackling one of the trickiest parts of software development. Code refactoring. You know those times when you have to make sweeping changes across multiple files?
Yeah, those are always fun,
Definitely not for the faint of heart, right? But for AI, it's even more challenging. It's not just about writing correct code, but also about understanding the big picture, planning a sequence of changes, and keeping track of everything that's been modified. And that's exactly what today's paper is all about.
It's called RefactorBench, evaluating stateful reasoning in language agents through code. Catchy, right?
Well, the title might be a mouthful, but the work itself is pretty groundbreaking. It introduces a new way to measure how well AI agents can handle this kind of complex, multi-file reasoning.
And spoiler alert, it's not as easy as it might seem.
So let's break down what makes this RefactorBench so special. First off, how is it different from the kind of code-related tasks AI has been good at so far?
Think of it this way. We've seen AI excel at things like code completion, suggesting the next few lines, or even finding bugs in single files. But refactoring, especially when it spans multiple files, is a whole different ballgame.
It's more like orchestrating a symphony than playing a single instrument.
Exactly. You have to understand how all the pieces fit together, plan your moves carefully, and adapt as you go along. That's where the idea of stateful reasoning comes in.
Okay, so stateful reasoning, that sounds like a fancy term. What does it actually mean in the context of AI and code?
It's all about keeping track of the changes that have already been made and understanding how those changes affect the overall state of the code base, just like a human developer would.
So it's not just about writing the next line of code, it's about remembering what you did 5 steps ago and how that impacts what you do next.
Right. And that's where many of today's AI agents stumble. They can generate brilliant snippets of code, but they often struggle to maintain a coherent view of the entire project as it evolves. It's like having a short-term memory problem you keep forgetting what you were working on.
And that's precisely what RefactorBench is designed to expose. It's like a stress test for an AI's ability to think like a programmer.
Exactly. And it throws some pretty tough challenges at them.
So tell me, what does a typical challenge in RefactorBench look like?
Well, they've curated a set of 100 real-world inspired code refactoring tasks, all pulled from open source Python projects, so we know they're the kind of problems real developers grapple with.
Okay, so real-world problems. That's a good starting point.
Yeah.
What makes these tasks particularly challenging for AI agents?
First off, each task involves making changes to multiple files. We're not talking about simple tweaks to a single function. These are substantial changes that ripple across a project.
How many files are we talking about? Give us a sense of scale.
The tasks vary, but some require modifying anywhere from 2 to over 30 files.
Wow, that's quite a range. And I imagine that makes it exponentially harder for the AI to keep track of everything.
Exactly. It really puts their ability to maintain context and reason about the overall state of the project to the test. And to make things even more interesting, each task comes with different levels of instruction: lazy, base, and descriptive.
So they're testing how well the AI can handle ambiguity, just like a real programmer might have to deal with vague requests from a client.
Exactly. The lazy instructions are very minimal, just a brief hint at what needs to be done. The base instructions provide more context and a clearer goal, and the descriptive instructions lay out the task very explicitly. This allows the researchers to see how much hand-holding the AI needs to succeed.
It's almost like giving them different levels of scaffolding to see how they perform. And that brings us to the question of evaluation. How do they actually measure whether an AI successfully completed a refactoring task in RefactorBench?
This is another area where RefactorBench really stands out. They've moved beyond simple code execution checks and developed these really clever AST-based unit tests.
AST-based, that sounds pretty technical. Can you break that down for our listeners?
AST stands for Abstract Syntax Tree. Think of it as a way to represent the underlying structure and logic of a piece of code. It's like a blueprint that shows how all the different parts fit together.
So instead of just checking if the code runs without errors, they're looking at whether the AI has actually restructured the code in the intended way.
Exactly. They're not just looking at the surface level, they're analyzing the deeper meaning of the changes. And this allows them to determine if the agent truly achieved the desired refactoring, even if the final code isn't an exact character-for-character match with a human-written solution.
That's really clever. It's like judging a translation not just on whether the words are correct, but also on whether it captures the true meaning and style of the original text.
You got it. And these AST-based tests are even more powerful because they're designed to evaluate not just the overall task, but also smaller subtasks within each refactoring. This gives the researchers much more detailed insights into exactly where the AI agents are succeeding and where they're tripping up.
So they have a microscope to zoom in on the AI's thought process, in a way.
Precisely. It's like being able to see the individual brushstrokes of a painting rather than just the finished artwork.
Okay, so we've talked about the challenges themselves and how they're evaluated. But I'm curious, how did the researchers actually go about creating these 100 refactoring tasks? Did they just handpick them from random open source projects?
Not at all. Creating RefactorBench was a multi-stage process, and it's actually pretty fascinating how they used both human expertise and AI power to build it.
Sounds like a good recipe for robust research. Tell us more about this process.
The first step involved using large language models, specifically GPT-4 to help identify potential refactoring opportunities within those Python code bases. They essentially asked these models to pinpoint areas where refactoring could be beneficial, giving them examples of common refactoring patterns to guide them.
So they use AI to help them find the raw material for the benchmark.
Exactly. But the AI didn't have the final say. The second step involved experienced human Python programmers who reviewed all the AI-generated suggestions.
A good sanity check.
Precisely. These programmers ensured that the proposed refactoring opportunities were valid and would genuinely involve changes across multiple files. They also used their expertise to judge the complexity and suitability of each task for this benchmark.
So it's a true collaboration between human and AI. What came next?
Well, once they had this curated set of refactoring opportunities, the next step was to create the gold standard solutions. This is where those human programmers really shone. They meticulously implemented the correct refactored code for each task. And interestingly, they actually used GPT-4 again at this stage.
Oh, that's interesting. Why bring the AI back into the picture?
They used it as a double-check mechanism. They wanted to ensure that the core refactoring tasks were, in principle, achievable by current language models. The idea wasn't to design tasks that were impossible for AI to solve, but rather to test their ability to plan and execute a sequence of steps to achieve a larger refactoring goal.
I see. It's about finding that sweet spot of challenging but not insurmountable.
Exactly. And this brings us to step 3, which is where those sophisticated AST-based tests come in. For each key change made in those human-written reference solutions, they created corresponding unit tests. These tests were carefully crafted to parse the underlying structure of the code and verify that the intended refactoring had been implemented correctly.
So they're not just testing whether the code runs, they're testing whether it's been restructured in a way that aligns with the goals of the refactoring task.
Exactly. And this level of granularity is what allows them to get really precise insights into how the AI agents are approaching these complex problems. And finally, in the fourth step, they generated those 3 levels of task instructions we talked about earlier. The lazy, the base, and the descriptive ones.
To see how well the AI performs with varying degrees of guidance.
Precisely. It's all about simulating the kind of real-world variability in task specifications that programmers often encounter.
So they built this really impressive benchmark that's designed to push AI agents to their limits in terms of code refactoring. Now, I'm dying to know, how did the agents actually perform?
Well, that's the million-dollar question, right? They focused their evaluation on SWE agent, which was known for its strong performance on other code-related benchmarks. They tested it with both GPT-4 and CLAW 3.5 Sonnet, 2 of the most powerful language models out there.
And drumroll, please.
The results were a bit sobering, to be honest. While there were glimpses of brilliance, the overall success rates were much lower than you might expect. For instance, when given the base-level instructions, GPT-4 only managed to successfully complete about 22% of the RefactorBench tasks.
22%. Wow, that's lower than I anticipated.
Yeah, it really highlights the gap that still exists between human programmers and even the most advanced AI systems when it comes to these complex, multi-step refactoring tasks. CLAW 3.5 Sonnet fared a bit better, achieving a 35% success rate with the most detailed, descriptive instructions.
So more guidance helps, but it's still a far cry from human-level performance. Did the researchers dig into why these agents were struggling?
They did, and that's where things get even more interesting. By carefully analyzing the step-by-step actions the agents took, they uncovered some really fascinating failure modes.
Failure modes. Tell me more.
One of the most surprising findings was that even when the instructions explicitly mentioned which files needed to be edited, the agents often failed to locate those files and make the necessary changes.
Wait, they couldn't even find the right files. That seems like a pretty basic step.
You'd think so, right? But it points to a breakdown in their ability to plan and understand the overall scope of the task, even when given seemingly clear directions. It's like giving someone a map to a treasure, but they can't figure out where to start digging.
A map without a compass. So what was another common pitfall they observed?
Another interesting failure mode was that agents often got tripped up by the need to introduce temporary errors in the code during the refactoring process. Now, experienced programmers know that this is sometimes necessary. You might need to make a change that temporarily breaks the code or violates style guidelines in order to reach the final correct solution.
Right, it's like taking a detour to reach your destination faster.
Exactly. But the AI agents often got stuck or gave up when they encountered these temporary red flags, even though they were part of a valid plan. It's as if they're too focused on generating perfect code at every step, and they lack the flexibility to embrace a bit of messiness along the way.
They're not comfortable with the creative chaos of refactoring.
Precisely. And the third major failure mode they identified was related to context overload. They observed that long feedback loops, especially those involving error handling or unexpected output, could really bog down the agents. It seemed like these loops would consume a significant portion of their limited context window.
Context window. Remind us what that is, guys.
Sure, it's essentially the amount of information the model can keep in mind at any given time. Think of it like short-term memory. And what they found was that these lengthy error handling cycles would sometimes cause the agent to lose sight of the original refactoring objective. It's like getting so fixated on debugging a small issue that you forget the big picture.
So it's a combination of short-term memory limitations and a lack of high-level planning.
Yeah, that's a good way to put it. And these findings really underscore the importance of stateful reasoning. If we want AI agents to truly master complex code refactoring, they need to be able to keep track of their own actions, understand how those actions impact the overall state of the code, and adapt their plans accordingly.
So how did the researchers address this challenge of stateful reasoning? Did they just throw their hands up and say, AI is doomed?
Not quite. They actually came up with a really clever solution. A state-aware interface.
Okay, state-aware interface. Break that down for us. What does that mean, and how does it help?
The basic idea is to explicitly provide the agent with a record of the changes it has already made to the code. They did this by adding a current state section to the agent's prompt, essentially a running log of its previous edits.
So like giving it a memory of its past actions.
Exactly. Before each new function call, they fed the agent this updated current state, reminding it of what it had already done.
And did this simple addition of a memory actually make a difference?
You bet it did. The state-aware version of SW Agent showed a remarkable improvement in performance. They saw an average increase of almost 44% in the overall task completion rate on RefactorBench.
44%? That's a huge jump.
It is. And the improvement was even more dramatic for those finer grain subtasks, where they saw a 71% increase in completion rate.
So just by giving the agent a way to remember its own actions, they significantly boosted its ability to reason about the evolving state of the code base.
Precisely. It's almost like giving the agent a notepad to jot down its progress. And this really underscores the power of state awareness in enabling more effective code refactoring.
That's fascinating.
Yeah.
It really highlights the importance of designing AI systems that can not only generate code, but also understand the context of their actions.
Absolutely. And this idea of a state-aware interface seems like a really promising direction for future research. It's like a missing piece of the puzzle that unlocks a whole new level of capability. But the researchers didn't stop there. They also introduced this concept of state update policies.
State update policies. Okay, now we're getting really fancy. What are those, and how do they build upon this idea of a state-aware interface?
Think of a state update policy as a more general and flexible way to manage and provide information about the state of the code base to the agent. The state-aware interface we just talked about is a simple example of this, where the state is updated by simply appending a log of the agent's own edits.
Just so a basic memory lock.
Right. But a more sophisticated state update policy could incorporate much richer information. For instance, imagine a scenario where multiple agents are working on the same code base concurrently, or where external processes might be making changes that the agent needs to be aware of. A well-designed state update policy could help the agent keep track of all these changes and adjust its actions accordingly.
So it's about moving beyond self-awareness to a broader awareness of the entire code base ecosystem. It's like giving the AI agent a real-time news feed of all the changes happening around it.
Exactly. And this opens up all sorts of possibilities. For instance, imagine an agent that can detect when another agent has made a change that conflicts with its own plans, and then proactively propose a resolution strategy.
That would be incredible. It's like having a team of AI programmers that can seamlessly collaborate and resolve conflicts on the fly.
That's the ultimate vision, right? And this research really lays the groundwork for that kind of future. Now, to really appreciate the significance of RefactorBench and this idea of stateful reasoning, it helps to zoom out a bit and look at the broader history of AI and software engineering research.
Okay, let's take that wider view. How does this work fit into the big picture?
For a long time, AI and software engineering tended to focus on smaller, more contained problems. Things like code completion, where the AI suggests the next few lines of code, or static analysis, where it scans code for potential bugs and vulnerabilities. These are incredibly valuable tools, but they're still relatively isolated tasks.
Right, they don't require the same level of holistic understanding as refactoring.
Exactly. But with the advent of these incredibly powerful large language models, we're now starting to see a shift towards much more ambitious goals. Researchers are exploring how AI can tackle larger, more complex tasks that involve reasoning about code at a higher level.
Tasks like refactoring, where you have to understand the intent behind the code and how different parts of a system interact.
Precisely. And RefactorBench represents a major leap forward in this direction. It's one of the first benchmarks that's specifically designed to evaluate an AI's ability to handle multi-file code refactoring. And the failure modes they've identified also resonate with some of the long-standing challenges in other areas of AI, like planning and reinforcement learning, where dealing with extended sequences of actions and maintaining context over time have always been major hurdles.
So RefactorBench is not only pushing the boundaries of AI and software engineering, it's also shedding light on some fundamental challenges in AI more broadly.
That's a great way to put it. And this idea of stateful reasoning in language agents has parallels in other areas of AI as well. Think about embodied AI and robotics, where an agent's ability to perceive, track, and understand the state of its physical environment over time is absolutely crucial for successful navigation and task completion.
So it's a concept that has implications far beyond just writing code. It touches upon the very essence of intelligent behavior, understanding and interacting with a dynamic world.
Exactly.
Okay, so we've covered a lot of ground here. Let's bring it back to our listeners. If they were to take away just a few key points from this deep dive, what would you want them to remember?
I think the core message is this. While large language models have shown incredible promise in many areas of code generation and understanding, tackling complex, multi-step refactoring tasks, the kind that require a deep understanding of the evolving state of a code base, remains a significant challenge. Current AI agents often struggle when they need to maintain context across multiple files and over longer sequences of actions.
Right, it's like they get lost in the maze of code.
Exactly. But here's the encouraging part. This research also demonstrates that by explicitly providing agents with a representation of their own past actions, what they call state awareness, we can achieve dramatic improvements in their ability to handle these complex refactoring challenges. It's almost like giving them a roadmap and a compass to help them navigate that maze.
No, there's a clear path forward, and it involves making these AI agents more aware of their own actions and how those actions shape the code base.
Precisely. And the development of specialized benchmarks like RefactorBench is crucial for identifying the specific limitations of these agents and guiding the direction of future research in this exciting field.
Because without a way to measure progress, we're just shooting in the dark.
Exactly.
And beyond the research world, what are some of the real-world implications of these findings? How might this research eventually impact the day-to-day work of software developers?
Well, I think the potential implications are huge. Imagine a world where AI tools can not only suggest code snippets, but can also autonomously handle large-scale code refactoring, freeing up human developers to focus on more creative and strategic tasks. And imagine these tools being able to collaborate seamlessly with human programmers, understanding their intent, suggesting improvements, and even proactively resolving conflicts. This research suggests that such a future might not be so far-fetched.
That's a really exciting vision. It's not about replacing human programmers, but about augmenting their capabilities and making them even more productive.
Exactly. And the state-aware interface offers a concrete path toward building such tools. Imagine AI-powered refactoring tools that can navigate the messy, iterative nature of real-world software development, where changes in one file might temporarily break things in another. These tools could help developers maintain a consistent and well-structured code base, even as the project grows and evolves.
It would be like having a super intelligent pair programmer who can always keep track of the big picture and make sure everything stays consistent.
That's the idea. And the concept of state update policies could be incredibly valuable in collaborative coding environments where multiple developers and potentially even multiple AI agents are working on the same project simultaneously.
It would be like having a team of synchronized swimmers all moving gracefully together.
Exactly. Each agent would be aware of the changes made by others, reducing conflicts and improving overall efficiency. And the reported cost and speed improvements seen in newer agent versions suggest that these technologies are rapidly becoming more practical for real-world use.
So it's not just a theoretical dream. It's starting to become a reality.
That's right. And now for our Novel Notions segment, where we take inspiration from the research and brainstorm some exciting, perhaps even a bit out there, ideas for future exploration.
The fun part. So based on this work on RefactorBench and stateful reasoning, what kind of new research directions are you particularly excited about?
One idea that I find particularly intriguing is to explore ways to make agents even more state-aware by going beyond simply logging their actions. What if we could develop techniques that allow an agent to proactively summarize and abstract the current state of the code base in a more meaningful way?
Okay, I like where you're going with this. More than just a memory log.
Right. Imagine an agent that can not only remember the changes it has made, but can also synthesize those changes into a higher level understanding of what's happening. For example, instead of just recording a series of edits related to different data models, it might be able to generate a summary like migrating all legacy database access functions for user and product models to the new ORM.
So it's almost like the AI is creating its own mental notes about the refactoring process.
Exactly. And these high-level summaries could be incredibly valuable. They could help the agent maintain a better grasp of the overall refactoring goal, prevent it from getting lost in the weeds of individual edits, and potentially even help it identify related refactoring opportunities that a simple edit log might miss. The research into gist-based memory systems suggests that understanding the meaning of changes can be more effective than just tracking the syntactic details.
It's like the difference between memorizing a list of facts and actually understanding a concept.
Exactly. And another research direction that I think is worth exploring is the development of what I call environmentally conditioned state update policies.
Environmentally conditioned state update policies. That's a mouthful.
I know. But the idea is pretty simple. What if the way an agent updates and reasons about the state of the code base could dynamically adapt based on the specific characteristics of the project or the nature of the refactoring task itself?
So a one-size-fits-all approach might not be the most effective.
Exactly. For instance, in a very large modular code base, the state update policy might prioritize tracking changes within specific modules, knowing that dependencies are more likely to be localized within those boundaries. Or for a refactoring task that primarily involves renaming variables, the policy might focus on tracking symbol usage across different files.
It's like having a customized toolkit for each refactoring task with just the right tools for the job.
That's a great analogy. And this idea of adapting the state update policy to the environment could lead to more efficient and contextually relevant state management, which could significantly boost the performance and scalability of these AI agents.
So instead of just giving the agent a memory, we're giving it the intelligence to manage that memory effectively.
Precisely. Now, of course, these are just a couple of ideas to spark further thought and discussion. Their feasibility and actual impact would need to be rigorously investigated.
As with all good research, right? It's about asking the right questions and then exploring those questions with an open mind. So, to wrap up our deep dive, it's clear that the RefactorBench paper provides a valuable new framework for evaluating how well AI agents can handle the complexities of software development, particularly in this realm of multi-file code refactoring. The challenges around stateful reasoning are significant, but the promising results from the state-aware interface offer a tangible direction for future research. We highly encourage you to check out the full paper. We'll include a link in the show notes.
And it leaves us with a fundamental question to ponder. As AI agents continue to evolve and become more adept at manipulating code, how will their ability, or perhaps their continued struggles with these complex, multi-file refactoring tasks, ultimately reshape the landscape of software development and the relationship between human and artificial programmers?
It's a question that's sure to spark many more deep dives in the future. Thanks for joining us on this exploration of the cutting edge of AI and software engineering. Until next time, keep those minds curious and those algorithms humming.